All right, so we want to talk about the greatest common divisor of a set of numbers. So let's say we have k numbers, n1 up to nkn. They're all natural numbers or counting numbers. Then we're going to say the greatest common divisor, or some people call it the greatest common factor. So you might see GCF instead of GCD. So what it is in the name. So it's a factor, but it's a common factor of each of our numbers. So it's a number D that is a factor of our first number, our second number, our third number, all the way to our kth number. And it's the largest factor that is a factor of each of these. So that's what we're looking for. All right, so let's do a little example just to see how to calculate this. So we want to find the GCD, or the greatest common divisor, of, say, 42, 294, and 132. So in order to do this, we're going to need the prime factorization. So it's a good idea to pause the video now and work out the prime factorization of these numbers. Okay, I'm going to write them down right now. So here's the prime factorization of our numbers here. Hopefully you could get that. If not, review tree factorizations and tree diagrams, and that should help you out. So let's see if we can work out what we'd need for a greatest common divisor. So looking at this, well, we need something in common. So the divisor that we'll pick out will have to be in common to all three of these. So if we think about it, well, we need to have the same primes in each of our three numbers here. So here we have 1, 2. Here's a 2. Here we have two 2's. But we can only take one of them as the common factor since it needs to be in all three of our numbers. Same thing with the 3. Well, here we have 1, 3. Here we have 1, 3. Here we have 1, 3. So we can take that 1, 3 as our common, part of our common factor. 7's, well, here we have 1 7, here we have 2 7's, but 132 has no 7's in its prime factorization, so there's no way that the common factor or common divisor can have a 7 in it. And same with 11. Neither of these numbers have an 11, so there's no way an 11 can be part of the greatest common divisor. So looking at this, well, we're going to take one of these 2's, and I'm going to circle the 2 without the exponent just to say it's one of them and not both, and the 1, 3, since that's what's in common with all of them. So it's going to be 2 times 3, which is 6. So 42 I can write, if you like, as 6 times 7. 294 is 6 times 49. And 132 I can write as 6 times 22. And that's the greatest common divisor. Now, can we come up with a good algorithm or a good kind of series of steps to determine a greatest common divisor? Maybe pause the video now and think about that. Think about how you would explain this to somebody if you were asked, what are the steps for finding a greatest common divisor? And I'll give you a little hint, or a good way of looking at it. Think about the exponents of each of your primes here. That's going to be a good thing to look at. All right, so now that we're back, let's write it down. So hopefully you've realized that what we're really doing is we're looking at each prime in a prime factorization for each of the numbers and looking at the exponents. And we're taking the minimum exponent out of the ones that appear. So let's write that down. To find the GCD of a set of numbers, let's say n1, n2, all the way to nk. So we're going to find the prime factorization of each number. Okay, and then the second thing is we're going to take the minimum, the smallest exponent for each prime in its factorization. The product of these is the GCD. And I should say by these, I'm being a little bit sloppy here, but by these, maybe I'll underline instead. By these, what do I mean? I mean the product of each prime to the power of the min exponent. So, again, let's look at this. So, using that logic, here we have an exponent. Let's look at the 2's first, I should say. We have an exponent of 1, an exponent of 1, an exponent of 2. So we have 1, 2, 1, 2, 2 2's. The minimum number of 2's is 1. That's the minimum exponent. So we're going to take 2 to the power of 1. What about 3? 3, we have an exponent of 1, an exponent of 1, an exponent of 1. So the minimum out of those is, of course, 1. Then we look at 7. We have 1, we have 2. But down here, we have no 7's. We have an exponent of 0. So we're going to have 7 to the 0, which is just 1, so we're not even going to include it here. And same with 11. The minimum exponent for 11 is 0. We have 0 11's in 42 and in 294, so we're not going to include any 11's either. And that is how to find the greatest common divisor. Take the minimum exponent of each of the primes in a prime factorization. That's the key. All right, and let's look at a related concept, but it's kind of from the other direction. So the least common multiple of a set of numbers is kind of the reverse problem. It's going to be a multiple of each of our numbers n1 to nk. It's going to be common, so it's going to be the same number for each of these guys, and it's going to be the smallest multiple that satisfies that. So it's the smallest number m, such that m is a multiple of n1, m is a multiple of n2, all the way to m is a multiple of nk. So, again, let's see if we can figure out how to do this. So we're looking for the least common multiple, and let's do the same number since we already have that prime factorization. 42, 294, 132. Here's the prime factorization of each. So, we know that m has to be a multiple of 42, so it has to be something times 42. So we need to write down 42 since it's something times 42. So we definitely need a 2, a 3, and a 7 in our multiple because it has to be a multiple of 42. So it's going to be 42 times some stuff. Okay, but it also needs to be a multiple of 294. So it needs to have a 2, a 3, and a 7 squared in there, or 2 7's. So we need 7 squared. So we need an extra 7 in there so far. And then we look at 132. Well, we need to have, it needs to be a multiple of 132. So it needs to have 2 2's, a 3, and an 11. Well, we already have 1 2, but we need a second 2 because it also needs to be a multiple of 132. And we need an 11 as well. So, inside of this number, we have 42, 2 times 3. In fact, maybe I'll write this down. So, we can view this, if you like, as 2 times 3 times 7. And then what do we have left over? A 2, another 7, and an 11. So it's a multiple of 42. Here's 42. I can also arrange it so it's a multiple of 294. So 2 times 3 times 7 squared. And then what do we have left over? We have a 2 and an 11. So we also have that it's a multiple of 294. It's 22 times 294. And we also have that it's a multiple of 132. We have 2 squared in here. We have a 3. We have an 11. And we have a 7 squared. So here is 132 in this number. Remember, all I'm doing here is I'm using the commutative and associative properties to rearrange this so that to show you that we have each of the numbers 42, 294, and 132 in here. So we can't take away any of these prime factors from this, else we wouldn't have one of these multiples. So this is the least we can get away with. And if we have any more prime factors, well, it's no longer the least multiple. If we multiply by anything, m will be bigger. So it's not going to be the least. This one is definitely the least, because if I get rid of any of these primes, then it's not going to be a factor of one of these numbers here. So that's the idea. We kind of build it up out of the prime factorizations that we have. So again, I think it's a good idea to pause the video and try and come up with a nice algorithm to determine the least common multiple of a set of numbers. Okay, hopefully you used the greatest common divisor algorithm as a nice blueprint. But again, we're looking at the prime factorization, and we're looking at the exponents of each of the prime factors. And what we're doing here is, rather than taking the minimum exponent for each of the primes, we're taking the maximum exponent for each of the primes, because we need to have the maximum number of primes that we have around, because it needs to be a multiple of every number. So if we look here, we have 2 to the power 1, 2 to the power 1, 2 to the power 2. So we need 2 2's in our least common multiple, in our LCM. So I take the maximum exponent of the 2's, which is 2. For the 3's, I have exponent 1, exponent 1, exponent 1. So I'm going to take the maximum of that. Well, that's just 1, so 3 to the power of 1. 7, I have 7 to the 1, 7 to the 2, and here we have no 7, 7 to the 0. So the max is 7 to the 2. So I'm going to take all 2 of these guys, and we look at the 11's, 11 to the 0, 11 to the 0, and 11 to the 1, so the maximum exponent is 1. So we're taking the maximum of each of the exponents for each prime. So let's write down to find the least common multiple of n1 all the way to nk. So first, just like before, find the prime factorization of each number, and then for each prime, include that prime to the maximum exponent in the least common multiple. So rather than the minimum for the greatest common divisor, we're going to take the maximum for the least common multiple.